Hello everyone, in today's Minecraft episode I'm going to be explaining the scientific term gravity and what it means in a scientific sense that is very, very close to reality and we can all picture it and imagine it. So let's go ahead. First of all, when we mention gravity, we need to think about two important people. The first of which is Sir Isaac Newton, and the second is Professor Albert Einstein. Now, we of course need to start with the guy who discovered gravity, or at least termed it gravity, which is Sir Isaac Newton. And we all know the infamous story of him lying down beneath a tree in his estate, and that apple fell upon his head. But he did something really counterintuitive, and he picked up the apple and asked himself a very, very important question. And he said, why did the apple fall on my head? Or why was it falling to the ground? Why didn't it stay stationary in the air? Why didn't it go sideways? Why didn't it go in loops, in circles? Why did it exactly fall down to the earth? So back at the time, he thought that there was this mysterious force that was attracting the apple to the ground, or it was this mysterious force that attracts two objects to each other, and that was his initial thought about gravity. And so he later came up with the term gravity, and then he proceeded to kind of prove it mathematically. And what he did is he basically came up with the formula to calculate the force of gravity in between two objects, and the formula was Fg equals g, the universal gravitational constant, mm over r squared. Fg, of course, being the force of gravity, g, the universal gravitational constant. The two m's are the masses that you want to, measure the force of gravity in between, and the r is the distance between them. Now, if you plug these numbers, if you plug this equation into anything gravity related, it can absolutely, with supreme accuracy, measure it without any problems, and this equation still works till this day. And of course, not to mention that Sir Isaac Newton had made up a lot of things in the scientific world that he's right now known as the father of modern science. And along with the force of gravity, he actually came up with the three formulas, or the three laws of motion. And all of those three laws of motion and formula of gravity, they work absolutely fantastic even to our day. But they all hinged on one simple idea, is that the space around us was real, but it's not really related to time. So there's no relation between space and time. So he pictured them as two separate entities. And he also mentioned that space was real, but it doesn't really have effect on anything, on mass or on time. And mass and time don't have any effect on space. Like picture it as a stage, and there's a play going on that stage. So what happens is that the play doesn't take any effect on the stage, and the stage doesn't affect the play in any way. So they're not really related. There's no correlation between them. And that was his initial thought and initial gist that hinges on the entire fact that he came up with the formula of gravity and the three laws of motion. And it was believed so up until Professor Albert Einstein came and took the reins from Sir Isaac Newton. And so in 1905, Professor Albert Einstein submitted 4 important papers to the scientific committee. The first one was about his famous equation, E equals mc squared, which basically means that energy can become mass and mass can become energy. And of course, E signifies energy, m the mass, and the c is the speed of light. And of course, this also explains, in practical sense, this explains how the sun can emit enormous amounts of energy. And of course, it was because due to its huge mass. So E equals mc squared is a very, very important equation in the scientific world. And then we have the electromagnetic effect, or the photoelectric effect. And this basically introduced the revolutionary idea that light is composed of both energy and particles. The concept that physical systems can behave both as waves, energy, and as particles, matter. Of course, Einstein later on in 1921 had won the Nobel Prize because of this very famous paper, and it was the beginning of the in a sense, it worked as a stepping stone for the entire of quantum mechanics or quantum physics about 16 years later. The third paper that Einstein submitted to the scientific committee was the Brownian motion, and is perhaps the least important out of the 4 papers that were published. But, and I'm quoting here, the paper is on the movement of small particles suspended in a stationary liquid as required by the molecular kinetic theory of heat. Now, I don't want to really elaborate on that because it's kind of, not related to gravity or even to special relativity. But what we want to talk about today was the third paper, and that paper was special relativity. Now, special relativity, and I'm quoting here, is on the electrodynamics of moving bodies. That's exactly how he actually presented that paper to the scientific committee. But what special relativity means is that the speed of light is immutable, constant, and independent of the observer's movement. Therefore, except for the constant speed of light, everything is relative, including time, distance, and matter. Now, what this basically means is that, counter to what Sir Isaac Newton thought, in the first place, that the space is not related to time and it doesn't really have effect on mass and time, and mass and time don't have effect on space. Einstein proved quite the contrary, because with his special relativity it was proved that space isn't just related to time. They are in fact one in the same entity, which scientists now call as space-time, and they do have effect on matter, and matter affects space-time. And basically, to picture special relativity in action, just imagine yourself in a wagon, and that wagon is moving and approaching the speed of light. Okay, and while you're approaching the speed of light and you're inside the wagon, now if you're looking out and you're reaching like 92-95% of the speed of light, you can see that the space-time around you, the space-time fabric, because it's malleable, because its structure is malleable and adjustable, you can see that the space around you is actually changing and adjusting and is bent, and it's kind of changing and adjusting just to keep you the speed of light constant no matter what. And of course, special relativity discusses like the relative terms or the relative perspectives, and I don't want to really get into it like a lot because special relativity is an important topic. I want to talk about general relativity. So after submitting all of these papers and after getting the praise for them and everything, Einstein wanted to tackle the most elusive force in the universe, and that was gravity. And he knew that the special relativity was inadequate and it was still incomplete, and it needed something to make it perfect. And that was the most abundant force in the universe. And that abundant force, of course, was gravity. And so when he first said it out loud that he wanted to tackle gravity, or the mysteries of gravity, everyone kind of looked at him and laughed and said that even the father of modern science, Isaac Newton, couldn't really grasp what gravity was, and you think you're better than him, or you think you can actually do what he couldn't. And so, of course, Einstein, proceeded to give them the middle finger, and then he went on with his search and studies. In 1907, he was working as a patent clerk, and he was in his office, and the window was open, and he looked out of the window into the opposite building, and he saw there were workers on that roof, and he had a thought experiment. And basically, a thought experiment is just like you having a thoughts, or you're experimenting with your thoughts, and you kind of create an alternate reality where you can control everything and just proceed to do whatever you want in your own mind. And that's kind of the thought experiment. Of course, he later on dubbed it as the most happiest thought of his life, or the most happiest moment of his life. And what happened in that thought experiment is that he imagined that worker on the roof falling down. So he fell down. He seemingly lost his balance and everything, and he fell down and he was plummeting to the earth. And while falling down, Einstein realized that the worker would not feel his own weight. He would be weightless. It's just as if you're in outer space. You won't feel your own weight. You still have your mass, but you still won't feel your own weight. And so he pictured that worker in a wooden box, and there was a beam of light shining from one end of the box and hitting the other. And now, if you want to actually picture this and put it in perspective, just imagine yourself riding an elevator and someone cut off the cord on top of the elevator and you were plummeting down with the elevator. And so what happens is that you won't be able to touch the floor of the elevator because you're going to be weightless, and you're going to be in between the ceiling and the floor, and you're going to be in between, and you won't feel your own weight. And what Einstein kind of thought of is that if there was a beam of light shining from one end and hitting the other, how would the worker view it? And of course, we all know that light only travels in straight lines. It doesn't go in zigzags, it doesn't go in loops, it only moves in a straight line. And so obviously the worker would view the beam of light starting from one end and hitting the other in a straight line, like anyone else should. But the thing is that from Einstein's perspective, when he's going to see the light, he's going to see it starting from one end and hitting the other after the worker and the box plummeted to the ground. And therefore, it will create a curve It will create a curve in the space-time fabric. And that, my gents, is exactly what the general relativity is and what gravity is. So gravity isn't this mysterious force that attracts you to the Earth. No, in fact, gravity is nothing more than the curvature of the space-time fabric being bent due to its malleable structure after a large mass is subjected to it. And let's put this in perspective. Now, let's just get an example of the biggest mass that is closest to us, and that would be the sun. Now, if we take the sun and we imagine that the space-time fabric is nothing but a two-dimensional plane, and just imagine it as a piece of paper, okay? And you take that piece of paper, and we know for a fact that that piece of paper is constructed from a very, very malleable subject or substance. And so what you do is you grab the sun, a very large object with a huge mass, and you place it on that malleable structure. So what will happen? What will happen is that the sun will create an indentation in the fabric of the space-time, and that indentation will be, portrayed or pictured as a curve, going around and around. Of course, just imagine it in a 2D plane, it will be easier to imagine. And so that curvature is exactly what gravity is. So we're not really stuck to the Earth because there's this mysterious attraction force between me and the Earth, or between you and the Earth. No, it's because due to the Earth's huge mass, okay, and it bending the space and time around it, we are actually being pushed down to the Earth due to the Earth's gravitational field. And also, if you want to realize why do planets orbit suns, or why does the moon orbit the Earth, or why do we orbit the sun, and it's basically because after you place a huge mass like the sun on this malleable structure, and after it creates a curvature in the space-time fabric around it, let's say that there's this solo planet that's it's operating on its own, it works solo and everything, and this planet comes inside of the sun's gravitational field. So what's going to happen is that the planet will go in, and it will follow the indentation and the curve created by the sun through the space-time fabric. So it's not moving in circles. In fact, it's moving in a straight line, but the line itself is a curve around the sun, and that, my friends, is exactly what curvature is. And given all of these facts, it is known that so Einstein had that thought in 1907, and it took him 8 years to actually come up with the mathematical formula to prove his general theory of relativity. So in 1915, Einstein finally confirmed general relativity with his mathematical formula, and of course then the scientific committee wanted some proof, some actual physical proof that what he's saying was true, and some studies were conducted and everything like that, but it wasn't proved until 1921 by some astronomers. They kind of predicted the shift that would happen to a certain star, and they had to actually observe it in a full solar eclipse, and it goes on and on, but basically, this is what gravity is. Gravity is nothing more than the curvature of the space-time fabric being bent due to its malleable structure. And that's all there is to it. And that's it for this video. Over and out.